All right, good people. This is the optional video for L'Hopital's rule. So you don't have to watch this. If you want, you can turn it off and go on with your day. You finished all the notes that you needed for L'Hopital's rule. However, this is a video to maybe show you where L'Hopital's rule comes from, and also to let you know a lot of people don't call this L'Hopital's rule. They call it Bernoulli's rule. And the reason is there's like controversy over who actually came up with this rule, right? And the story is that L'Hopital, who that's the guy's name, Guillaume L'Hopital, de L'Hopital, I think is his name, was this aristocratic. I think he was like in the military. He was like a lieutenant general in the military in France, but he retired, or he had to retire, and then he had like all this time, all this money, and so what he would do was he would hire people to kind of tutor him in some of the classics, if you will, and mathematics being a big deal back then. He would hire tutors to help him kind of learn new things and study things. And one of the tutors was one of the Bernoulli brothers, and I think it was Johann Bernoulli. There were like three or four Bernoulli brothers, and they all came up with the Bernoulli principle in physics. I think is one of the Bernoulli brothers. But one of the Bernoulli brothers was his tutor, and it's come out since then that I think L'Hopital, because he had money, offered Bernoulli this deal where if Bernoulli came up with a new idea, he wanted to be the first one to know about it. So he would pay him a certain amount of money every year. And if he came up with a new mathematical idea, or he heard of something, he had to be the first one to know. He couldn't, Bernoulli couldn't share it with anybody else. Like he had first right of privilege for that information. What Bernoulli didn't know was that L'Hopital was putting together a textbook, and he was putting all these ideas in there. And so he put this idea in his book, and that's why it's called L'Hopital's rule, because L'Hopital wrote the book. However, there's controversy over whether he really came up with it, or was it Bernoulli that came up with it and basically sold him the idea when they came up with that little pact of sharing mathematical information. So it just goes to show you, like, 400 years ago, like this is math was like was a TikTok of the time where people would share things, math ideas, math theorems, these new discoveries. They would share them with each other instead of sharing TikToks. They would share this. But the big idea is we have it now. So whether it's Bernoulli's rule or whether it's L'Hopital's rule, this is a rule that can help us out. But where does it come from? So some people say it's related to, one way to think about it, I guess I should say, one of the ways it's related, one of the ways we can prove it is because it's related to what we were talking about with the tangent line, right? The equation of the tangent line. And so this is one of the limits that we already did. But you'll notice that this is not a polynomial function. This is an exponential function mixed with a polynomial function. So it's kind of a mixed function, and it's not really workable because it's has an e in it, right? Just like if it had a sine in it or a cosine or a tangent, then it would not be a polynomial function. So if you recall, what we said was the tangent line is very close to the actual function, which I'm boxing in orange, near the x value, near the point of tangency. So my point of tangency is x equals 0. What I would like to do is find the equation of the tangent line of this orange function. How do we do that? Well, we need three things. We need an x-coordinate, which we have. We need a y-coordinate, which we don't have, but we can substitute 0 into the formula to get that. And when you do that, that's 1 plus 0 minus, oh, that's 0. Well, that's nice. And we need a slope. And in order to find the slope, we need the derivative. So the derivative is e to the 2x times 2 plus 1, except we know we want the slope when x equals 0. So if I substitute this in, this would be 1 times 2, which is 2, plus 1 is 3. That would be the slope. So what I'm going to do is I'm going to replace this with the tangent line. a tangent line that says y equals m times x minus x1 plus y1. Why am I doing that? Because we said that the tangent line is a good approximator for x's that are close to the point of tangency. And if I'm treating my point of tangency as being zero, that's because my limit is getting closer and closer to zero. So as I get closer and closer to zero, the approximation is going to get even better and better and better until I get to zero, and it's going to be the exact same thing. Okay, let's keep going. So now, instead of doing this, I'm going to do the limit of this equation of the tangent line over the bottom. So that's going to be the limit as x approaches 0 of, really all of this is just 3x, right? Over x squared plus 4x. Well, that didn't really help because if I substitute 0 in the numerator, I get 0. 0 in the denominator, I get 0. However, I can factor out an x from the denominator. And now I can do like a little algebra step. And then I'm left with 3 over x, just x, plus 4. And now when I try to do direct substitution, I'm going to get the answer that we wanted. So the idea here is we can use the tangent line approximation because my limit is getting closer and closer to that point. If I use a tangent line approximation, it's going to get closer and closer to the actual y value, so it's going to work. And I can use the tangent line approximation as a way to find that. Okay, so then let's remember that the formula is y equals m times x minus x1 plus y1. But let's put it in terms of derivatives. So that's y equals f prime at some number times x minus x1. And really, x1 is that some number, plus the y value, which is f of that number. This is the way we think about it. This is another way to write it, right? If you have a function, you plug in this x value into the function to get the y value, and then you take the derivative of that function and plug in this x value in order to find the slope. Awesome. Now, so L'Hopital's rule says if f and g are differentiable, so I got to be able to take the derivative, and f evaluated at c is 0. I'm sorry, that's not true. It says, and if the limit as x approaches c of f of x is equal to 0, and if the limit as x approaches c of g of x is equal to 0, right? If I take the limit of the top and it equals 0, and if I take the limit of the bottom and it equals 0, then I can use L'Hopital's rule. So this has to be true in order for me to do L'Hopital's rule. But here's a nice thing about this step. If I'm taking the limit as x approaches c of f of x over g of x, we can write the tangent lines for these two functions, and it would look like this. And I could do the same thing for g, and it would look like this. And we know that f of c has to be 0 because the limit of f of x as x approaches c is 0. And because it's differentiable, we know it's continuous. So therefore, whatever the limit is, that's what the y value is. So this has to be 0, and this has to be 0. So then we're going to be left with this. Oh, sorry. Because if these are 0, they're gone. And then once I get to this point, hey, x minus c and x minus c are going to reduce. So then I'm left with this. And this is now showing where I started the limit of two functions, if their individual limit on top and bottom go to 0, is going to equal this limit, which is just the derivative of the top evaluated at the x value that we're approaching over the derivative of the bottom evaluated at the x value we're approaching. And so this kind of gives us a a connection back to tangent lines as a way to prove L'Hopital's rule that it does work, right? So that's awesome. And it's not the only way to show it. Here's another quick way to show that L'Hopital's rule. Again, we have the conditions, right? So these are the conditions. We have to have the functions being differentiable, and we have to know that the limit of the top function f of x goes to 0, and the limit of the bottom function g goes to 0. So what if I have this? C of f of x over g of x. If that's true, then this is true. Plus 0, minus 0. And minus 0. Obviously, that's true. It seems a little redundant, but that is true. However, what if I say this is f of c, and this is g of c? How do I know that that's true? Because we said as part of the conditions that the limit of f of x as x approaches c is 0. So the limit as x approaches c of f of x or f of c is 0. So therefore, f of x is 0. Therefore, f of c has to be 0. Okay, so far, this line of thought should make sense. But now I'm going to divide the top by something, which is okay as long as I divide the bottom by the same thing, right? So we're going to take the limit as x approaches c of. So I'm going to divide the numerator by x minus c. As long as I divide the denominator by the same thing, it turns out to be equivalent. An equivalent limit to the previous limit, right? Except once I get to here, if I take the limit of the top, this formula should be a familiar formula. This was one of the forms of the derivative, the limit definition of the derivative. This was one of the forms. So therefore, this whole thing in the numerator equals f prime of c. And the same thing on the bottom. The limit as x approaches c of g of x minus g of c all over x minus c. That is the definition of g prime of c. And so we now have that in order to find the derivative, in order to find the limit of f of x over g of x as x approaches c, take the derivative by plugging in c, the x value that we're approaching, over take the derivative of g and plug in the x value of c in order to figure it out. Two different ways to look at it, but both of them will give us that, or maybe help us understand a little bit better that L'Hopital or Bernoulli really knew what they were doing here in order to find a shortcut rule for us.